So this is a joint work together with the colleagues from Boston and Herzegovina, but they are not present here, and I was asked to present this our joint common work. So the topic is actually the testing, fracture toughness testing and material properties testing of the pressure vessel. This is actually the air vessel, which was used for quenching machine with 1,000 tons of power for the pressure. And it was in the service, it was built 70 years ago, and it was in the service about 50 years. During the inspection, they find the cracks, and the idea was actually try to see what's happening in this material. Dimensions you have presented here. It was long, more than 4 meters, and it was quite thick pressure vessel, and it was made from manganese steel. So from this pressure vessel, it's made like one piece, and it was used machining the specimens from different parts. From here you can see from the bottom vessel. Here is from the wall, from the middle, and also you can see here is from the top. So how it's thick, and where we found the cracks. Actually, you can see these dimensions in the centimeters here. So we have the set of specimens to characterize material properties of this material, and you can see the range test for the tensile test, for sharp toughness, and also for fracture toughness testing according to standards. First, we did also some metallography on this inspection. We got some difference in metallography in microstructures regarding the place where the samples were taken, and also we can see that this can also have some effect on the fracture toughness and other properties. So here you can see the results of fracture toughness testing on the different temperature also and from different area. And also you have here is the standard tensile test results getting from the standard tests. Also here you can see the chemical composition of this material, which was done from the samples. Here with the testing of fracture toughness, we used the 3-point bend specimens, and we observed the surface also by armies, and also we put here the clip gauge according to ISTM 1820 standards. So you can see here that it's actually ductile, still ductile material, and we have for each of place we have 3 specimens, and when we tested, we got this low displacement curves and this resistance curves. I apologize for this. From this kind of presentation, it disappeared these remarks. Sorry. So you can see that we actually tested different geometry of specimens, dimensions. We have from this area like yield strength, and also for each of these specimens we measure the fracture toughness values. Also, if you use the calculated formula for linear elastic, we can assume the critical crack length for this material. But in order to get reliable results, we should apply some statistics. And as you know, very powerful is the walle distribution, especially in the case when you have only few specimens. At least you should have 3. But here we use this walle distribution, whereas the I is the current number of specimens, and N is the total number of specimens. And here we have this walle distribution, where you use the current value measured by fracture toughness test. This is the value of fracture toughness, whereas the probability is 0, and this is the mean value, whereas the probability is about 64%. So when you put all these experimentally measured values, we have here 3, and if you use this formula, you can calculate through this point. You get the viable distributions, and from this distribution you can get the lower bound and upper highest value with in the probability range of 99%. We did all for this all 3 types positions of specimens, and if this line is more narrow, of course, then we can say that the results are more reliable, and we can trust to these results of fracture toughness testing. In this case, we have some more specimens, and of course our results are more reliable, that we can trust in these results we can use in the fracture toughness testing procedure, as was used in FitNet, mentioned before, or CINTA procedure, or PS7910 procedure 2. So here we can see that in the case of top, that our interval for 3 specimens is quite bright. It's not so narrow that it means that in this case it's necessary to repeat the more tests to get the more reliable results. So the conclusion is that analysis of results according to location gets the different values. Also, it is connected with the different microstructures too. And this research really demonstrated that large structures, where it's not possible to take the samples without distortion, we need to use actually the material properties correctly, or by simulation, or by different techniques. Also, statistical analysis obtained showed that we can trust the still to viable distribution, and for each region we should find our own distributions parameters. Thank you very much.